Hello and welcome to our lesson on roots of complex numbers. And before we get into the concept, I want to just have us look at this equation for a moment, x cubed minus 8 equal to 0. If I told you or asked you to solve x cubed minus 8 equal to 0, you're probably thinking, well, let me just solve this by getting x alone because I know the inverse of the two operations that are shown in the equation. So I might start by adding 8 to both sides, and so then I'm looking at x cubed equal to 8. And then maybe I take the cube root of both sides, because the cube and the cube root cancel, leaving me x all by itself equal to the cube root of 8 ends up being 2. Now 2 is one of the solutions to this equation, but it is not the only solution to this equation. Our fundamental theorem of algebra says that the degree of our equation dictates the number of complex solutions that exist. So if our polynomial equation has a degree of 3, there should be 3 complex solutions. If we had a degree of 4, then we should have 4 complex solutions. Now remember, every number is a complex number, but some of those complex numbers only have a real number component. Some of those complex numbers only have an imaginary number component. So the solution that we found here is one of the 3 solutions, and it happens to be a real solution. It has a 0 imaginary component. That means that the 2 solutions that are remaining for this equation, again, still complex solutions, 2 is a complex solution, it's just only got the real component. The other 2 complex solutions are non-real or imaginary solutions. So what are the ways we can find them? Now, first, I want to show you this x cubed minus 8 graphically. This is another really easy way to find real solutions. If I looked at x cubed minus 8 graphically, that one real solution at 2 is the one place where that graph intercepts the x-axis. So again, we can quickly solve this by getting x alone. We can quickly graph this and see where the graph crosses the x-axis. Both of those lead us to the one real complex solution, but the 2 remaining complex solutions that are non-real or that are imaginary, we have to have other options for solving. Now for this particular equation, hopefully we're thinking about another option for solving, because x cubed minus 8 is actually factorable. This is a difference of cubes. It would factor into an x minus 2, and then x squared plus 2x plus 4. So if I wanted to solve this, because it's in factored form, it's actually not too bad. X equals 2 is my one real solution, just like I found here, and then I could use the quadratic formula or completing the square method to solve to find the remaining 2 solutions here. And again, those remaining 2 solutions would be imaginary. But the option of factoring isn't always available. Think about if we had something that was a higher degree or that just wasn't factorable. Like if we had, let's say, I don't know, an x to the 6th power plus 24 or something like this, where this isn't going to be factorable, and I know there are 6 solutions, but if I look at x to the 6th plus 24 on a graph, then none of them show up graphically, so this thing never touches the x-axis. So how do I get all 6 of them when they're all 6 non-real? So this is what I want to show you today, an option for finding the non-real of our complex solutions. I don't know why I erased that, because I'm going to go back here anyway. So back to this. Again, our fundamental theorem of algebra says that this particular polynomial equation, again, the one we're focusing on for a second here, and I'm focusing on this smaller degree because the work is a little bit intense, so I want to keep it simple for our first example. So again, this polynomial equation with a degree of 3 has 3 complex solutions or roots. So we tend to use those words a bit interchangeably. 3 complex solutions or roots. One of the roots we can find really easy. Graphically I showed you, algebraically I showed you by getting x by itself. It is the only real root that exists for this, the only real solution. And again, that was at x equals 2. The 2 remaining roots are non-real. And although we could find them by factoring, that's not always going to be an option, so I want to show you how we can find them using an extension of De Moivre's theorem. I have a really hard time with that name, sorry. So, let's consider this. When we are saying that x cubed minus 8 is equal to 0, again, I could move that 8 over and say x cubed is going to be equal to 8. Okay, there are 3 different values of x that I could cube to get 8. That is, there are 3 complex solutions. 3 complex numbers I could cube to get 8. I found one of them. I know that 2 cubed makes 8, but what are the other 2? Okay, let's pretend I didn't have the one real solution yet. Okay, if I can cube 3 complex numbers to get 8, then I can rewrite that again using our polar form of a complex number. So again, we're saying x cubed, oh, I don't need to write this, I wrote this up there. If I have 3 different numbers I can cube to make 8, and again, those are going to be complex numbers. So remember, the polar or trig form of our complex number is r times the cosine of theta plus I times the sine of theta. There are 3 of these complex numbers that I could cube to make 8. And here's where our theorem comes from, or is going to be put into play. Now I have a complex number raised to a power, and actually I'm going to condense this. I'm going to call this r cis theta cubed. I'm going to apply my power theorem here and say that now r cubed and cis 3 theta is going to equal 8. So remember, when we have a complex number in that polar form raised to a power, we're going to raise the radius to that power, and we're going to multiply our angle by that power. And actually, I need to back up a little bit here. I want to call this angle something else. I'm going to call it alpha because theta is going to come in later and I don't want to confuse my angle. So I'm just going to call it alpha, but same process, okay? So here we are, stuck at this point. 2 variables in one equation I cannot solve for. However, instead of trying to worry about this side of the equation, what I'm going to do is focus on manipulating this side of the equation. So 8 is the same thing as 8 plus 0i. So if I'm looking at that 8 in its standard rectangular form, then from that standard rectangular form, I can find the radius and the angle attached to its trig form. So I'm going to take the rectangular form of 8 and find its trig form. So the radius, I know, is the square root of x squared and y squared. In this case, that's going to make the square root of 8 squared, which is just going to be 8. So I know I'm going to have a radius length of 8, and I know that my angle, theta, and this is why I changed my thetas up there to alphas, because this is a different angle that I'm looking at, is going to be equal to the inverse tangent of my y value of 0 over my x value of 8. So I'm looking for an angle where the tangent of my angle is 0. So I have a tangent of 0 when my y value is 0 and y is going to be 0. And in quadrant 1, because everything's positive here, so y is going to be 0, and in quadrant 1 at 0 degrees. So 0 degrees, 360 degrees, really any angle that's coterminal with 0. So at 0 or any coterminal angle. So 0, 360, 720, and so on. Okay? So now, what I'm going to do is, a little trickery here, I'm going to replace the 8 with what it's equal to, which is going to be our r cis theta. So in this case, I can rewrite this. I have the r cubed cis 3 alpha on one side, and on the other side, in place of 8, I'm going to put its polar form, which is going to be 8 cis 0 degrees. Okay? Which now helps me to solve. I can see if these two forms have to be equal, that the r cubed that's here has to be equal to the 8 that's here. And let me change colors. The r cubed that's here has to be equal to the 8 that's here. And I can also see that the 3 alpha I have here has to be equal to the 0 that I have here. But let's see, if I take that to the next step, again, r cubed has to equal 8. I can now take the cube root of both sides, which means r is the cube root of 8, or 2. And then here, I can say that 3 alpha has to equal 0 degrees. Now, remember, that's really 0 or anything that's coterminal with 0. So I'm going to add 360 to this k times, where k just represents some integer, and we've done that before. We've just used the variable n, but I don't want to use n here because that's going to come into play later. So I can add 360 once, or 0 times, or 1 time, or 2 times, or 3 times, or negative 1 time, or negative 2 times, any number of times, and end up at the exact same angle. So I'm going to put that in there. Now if I wanted to solve this one for alpha, like over here I solved by taking the cube root. Over here I'm going to solve by dividing both sides by 3. So my alpha has to be equal to 0 degrees plus 360 degrees times some integer k divided by 3. Now what am I going to do with this is figure out, remember we're looking for 3 complex solutions. So I know the radius length at the complex solutions, and I know different angles at the complex solutions. So let me just figure out what they're going to be. Okay, so let me wrap this maybe up here. Okay, let me go up here with this. Let's say I wanted to figure out what's going to happen when k is equal to 0. Okay, if k is equal to 0, then my angle alpha is going to be equal to, so if I put a 0 in here for k, my angle is going to be equal to 0 degrees plus 360 degrees times 0, and then we would divide by 3. So one option for my angle is just 0, right? We got 0 on top of everything there. 0 and 360 times 0 is still 0. 0 divided by 3 is still 0. Okay? So one option for one of my solutions is I have a radius of 2 and an angle of 3. Right? Remember my complex solution in this form. Another option is, well, what if my k is not 0? Maybe my k is 1. So let me put k equals 1 in here. Okay, what's alpha going to be if k is 1? So 0 degrees plus 360 degrees times 1 divided by 3. So in this case, 360 divided by 3 would make 120 degrees. So another option for a complex number here would be, again, a radius of 2 and an alpha of 120 degrees. Or maybe I say k is equal to 2. So then alpha would be 0 degrees plus 360 degrees times 2 divided by 3. So that would be 700, well, let's see, 360 divided by 3 is 120, and then if we double that, we're going to get 240, so alpha would be 240 degrees. Okay, so another option for my complex solution that I'm looking for is my radius is 2, and my alpha is 240. Now, how far do I need to keep going is really no further at all. So I know I'm going to stop here for a couple of reasons. One is that I'm looking for 3 different complex numbers. I've already picked my 3 values for k to get those 3 complex numbers. But if I was to continue in either direction, picking negatives or picking positives, what's going to happen, and don't write this down if you're taking the notes, when you go to plug in k equals 4, okay? Alpha would be 0 plus 360 times 4 divided by 3. So 120 times 4 is going to be 400 and... oh, hold on. I can't. Oh, why did I skip to 4? Just kidding. The very next number after 2 would be 3. I'm like, this is not working out. So this, I want to be 3. Once I get to my very next number of 3, I end up with my alpha being 360 degrees. And 360 degrees is exactly the same place as 0, so it's really no different. I don't need to repeat that. And then if I go to 4, I'm going to end up being at the same place as 120, so I don't need to repeat that. So once you get past your first 3, you end up with the same pattern of repeating angles. They're all so all the angles would be coterminal to the 3 that we've already found. So there's 2 reasons I know to stop. 0, 1, and 2 are going to be our values for k. We'll always start at 0, and we're always going to stop at 1 less than our root that we're looking at. And I meant for that to be, our root that we're looking at is 3. So I'm going to go 0, 1, and 2. If our root was 4, I'm going to go 0, 1, 2, and 3. If our root was 5, 0, 1, 2, 3, and 4, and so on. Okay? So these are my alphas. Now again, let me just write out what those complex roots are going to be. So my complex roots, my solutions, okay, are going to be based on those angles. I can say x would be equal to 2 cis 0 was the first angle. X is going to be equal to 2 cis 120. That's my second angle. And then x is equal to 2 cis 240. That I said 240 and I wrote 40. 240. Right, that was my third angle. Those are my three complex solutions. Now that would be the trig or polar form of those solutions. If I wanted the rectangular form of the solutions, then I would have to evaluate each of these. So x would be equal to, this would be 2 times the cosine of 0 and then I times the sine of 0. Well, the cosine of 0 is 1 and the sine of 0 is 0, so this would be 0i, and that means x would be 2. Well, that's the one solution that we found graphically anyway, okay? And then for the next one, this would be 2 times the cosine of 120, which is a negative 1/2. And then the sine of 120 would be radical 3 over 2, and that one's going to be imaginary. And so this ends up being negative 1 when I distribute in the 2 plus radical 3i. And then the third one would be twice the cosine of 240 is a negative 1/2. And then the sine at 240 is a negative radical 3 over 2. I'm trying to squeeze all this in here. Negative radical 3 over 2, and again that one's imaginary, and if I distribute in the 2, it's going to be a negative 1 minus radical 3i. And those would be all three of the solutions. Again, all three being complex solutions, but one which is a real solution, and then two which are non-real. So non-real, or we could say imaginary. But all three solutions nonetheless. Now this is definitely more work than having to, let's say, use factoring as an option, but again, factoring isn't always an option. So what does this boil down to in terms of a formula, and how can we use this moving forward? Well, if we are looking for the nth root, that's what we're doing here. What we're doing here is finding out what are all the different things that I could cube to get 8. That is, what are all the cube roots of 8? So 2 is the real cube root of 8, but the other two are also cube roots of 8. The other two non-real things we found are also cube roots of 8. So we're finding the nth root of some complex number. In this case that we worked on, we found the cube roots of 8. But in general, if we have some complex number, we'll call it z, okay, in our polar form, then they're going to be exactly n distinct nth roots. So if I wanted to know the nth root of z, what I need to do is take the nth root of the radius, right? So the nth root of the radius, we did that over here, we got 2, and then we're going to multiply it by the cosine plus in the imaginary and the sine of alpha. Now, that's what I called alpha up here, but that ends up being whatever our angle was plus 360 degrees times some integer. So k represents an integer, and with that value of k, what we're going to plug in is starting at 0 and then ending at n minus 1. So n is our index of our root here. If we're looking for a fourth root, then this would end at 3. If this is a fifth root, then this would end at 4. Okay? And I mentioned that a few minutes ago. And n, that same value of n, is what we divide by here. Okay? Now that might look a little bit complicated, but let me just try to show you with the next example. Hopefully this is making a little bit of sense. How we can apply this. So let's try to use our theorem. Let's try to figure out the 2 square roots of 4i. So this is not in the context of solving here, but any complex number is going to have a distinct number of roots for whatever the root is. So it would have exactly 2 square roots, or exactly 4 fourth roots or exactly 7 seventh roots, and so on. So this is saying find the 2 square roots, and it wouldn't be like 3 cube roots because it doesn't make any sense, right? So whatever your index is, that's how many roots they're going to be. So if I want to find the 2 square roots of 4i, how do I start this? Well, I want to try to apply this formula, this nth roots theorem, but I need for my complex number, which right now is given to me in this rectangular form, I need to put it in our trig form, okay? So first, I'm going to say z, the complex number that we are looking at, is 0 plus 4i, okay? Which means that the excuse me, the x component is 0, the y component is 4. So if I wanted to find the radius, square root of 0 squared and 4 squared is going to make 4. And that should make sense because our x component being 0 means we're not going to move left or right. Think about this graphically. If our y component is 4, we're just going up 4. So yeah, we have a radius of 4. And our angle should also make sense. Remember, we can find our angle using the inverse tangent of our y value over our x value. Now that fraction is actually undefined, but if, again, think about where 4i is located graphically. If we just go up 4, so I'm saying this, if our vector goes here, up 4 units, so up 4 units, then our angle has to be 90 degrees. That's where we have a 0 for cosine at 90 degrees. Okay, so even though that fraction is undefined, I know that my angle is going to be 90 degrees. Okay, so when I am trying to find what it's asking for here, I'm trying to find the square root of 4i, the square roots of 4i. There are going to be 2 of them. I know that those square roots of 4i will be equal to, according to my formula, the nth root of r. So in this case, it's going to be the square root of r we just found was 4. And then we're going to multiply by cis of this craziness in here. So we're going to take our angle. We found our angle was 90 degrees. But remember, that's just one way to classify that angle. I can keep adding 360 any number of times to land at the same place. So now to that I want to add on 360 degrees k times, and then that's going to end up being divided by n. And n is going to be 2 because it's a square root. If it was a cube root, it would be 3. If it was a fourth root, it would be 4, and so on. Okay, so this is what it looks like plugged directly into my formula. And again, we're going to be figuring out our angles, or let's call them alpha, for, I need another color, for k equals 0 and 1. So we'll start at 0, always start at 0 for k, and then because we need 2 square roots here, we only need to go to 1, so we need 2 different values of k. Alright, so hopefully that makes sense. So for alpha, I need another color here. How about purple? So for alpha, we're going to take our angle of 90. We're going to add 360 degrees 0 times and divide by 2. And that's going to make, let's see, 90 divided by 2 is 45 degrees. And then for our second option for alpha, we're going to take our 90 degrees and add 360 times a k value of 1 divided by 2. So 360 and 90 would be 450 divided by 2 is going to be 225 degrees. And now I'm going to know the polar form for my complex roots. So we can say that the square roots of 4i are going to be equal to, my radius is the square root of, or it's the nth root of my radius, so the square root of 4 is going to be 2. So it's going to be 2, and then cis, one of my angles is 45 degrees, or I have my radius of 2, and then the other option for my angle is 225 degrees. And so if I asked you for the 2 square roots of 4i, here they are. These are my 2 roots, but these are in polar form or trig form. And we need to be able to handle either one. I think one question in your homework I said leave them in trig form, but another one I asked you to put it in rectangular form. So if we needed the rectangular form, then we just have to evaluate these. So this would be 2 times the cosine of 45, which would be radical 2 over 2, and then I times sine of 45, which is also radical 2 over 2, and then we multiply in that radius of 2, and we end up with 1 radical 2 plus radical 2i, or I radical 2. Okay, and then the next one would be 2 times the cosine at 225 is going to be a negative radical 2 over 2, and the sine at 225 is also a negative radical 2 over 2. And again, multiplying by 2, we're basically getting the same thing, but we're going to have negatives here. So a negative radical 2, and then a minus radical 2i. And these would be my complex roots in rectangular form. And we're good. Okay, so we're finding the square roots of 4i, and there they are. Alright, and the process we're doing here is just the same process that we're looking at here, again, ultimately to be able to solve, but I just wanted you to kind of get a feel for the formula, and then I'll show you another one again where we actually want to be able to use it to solve. Okay, so look at number 2. We are asked to find all 4th roots of this complex number, and again, we're going to try to write those roots in rectangular form. So first, I want my trig form for this complex number. Okay, so my trig form for this complex number. First, I'm going to say colors that I'm start with blue. Okay, so first I'm going to call this complex number z. So we have a negative 8 plus 8i radical 3, which means my x component is negative 8 and my y component is 8 radical 3. So if I wanted to find my radius, again, to try to get my trig form for this complex number, it's going to be the square root of negative 8 squared and 8 radical 3 squared. And if you wanted to just use your calculator to avoid some of this work, your calculator's happy to do it, especially because I know this is going to work out. If you put it in your calculator and you get a decimal, then you're not going to want to keep that decimal. You're going to want to do the work by hand. But if it works out to be a nice whole number, then the calculator can help us bypass some of the work. That's kind of a nice feature sometimes. So underneath the radical, 8 rad 3, and then that quantity squared, yeah, ends up being 16, so that's good. Alright, so that was, I mean, if you did the work, this is 64, and then this is really 64 times 3, and so we end up with 192 and 64, which is 256, and the square root of 256 is 16. But the calculator did it, okay, so we're good. And then our angle is the inverse tangent of our y value over our x value. So our y value of 8 radical 3 over our x value, which is a negative 8. Now technically, I need another color. Let's go with orange. If I'm looking at this, I can reduce those 8, so I'm really looking at a radical 3 over a negative 1. Remember, that means we're looking at a radical 3 over 2 over a negative 1 over 2. So our coordinates would be a negative 1/2 and a radical 3 over 2. And that is going to happen at a 60-degree reference angle in quadrant 2, so 120 degrees. Okay, so I know our angle is going to be 120 degrees. Okay, so now I think we have all the information we need to be able to plug into our formula. So the formula says if we're going to take the nth root of z, in this case we're going to take the 4th root of rz is a negative 8 plus 8i radical 3. It's going to be equal to the 4th root of our radius, which we found was 16, And then we're going to multiply that by cis of our angle, 120 degrees. And then we're going to add on 360 degrees k times. We're going to find the coterminal angles till we get to the first 4 of our solutions. And then we're dividing by n, which again, it's the 4th root, so we're dividing by 4. So that's going to be the form of our solutions. And we're going to do this for k equals 0, 1, 2, and 3. Those first 4 values of k will get us those 4 complex solutions that we're looking for. Alright, so now we got to figure out what those angles are. So I'm going to call them alphas. So alpha is going to equal 120 plus 360 times 0 over 4. And that's just 120 divided by 4, which is going to be 30 degrees. And then another alpha is going to be 120 degrees plus 360 times 1 divided by 4. And so 360 and 120, that's 480 divided by 4 is going to be 120. And then I have to plug in for k, I got to plug 2 in. So 120 degrees plus 360. And ultimately, if you could use some of this in your calculator, it's like type it in there and then just replace those values and be a little quicker. That's totally fine. I just don't want anyone getting lost. So 720, 820, 840 divided by 4 is going to be 210. And then lastly, we're going to plug in a k value of 3. So 120 plus 360 times 3 divided by 4. And that's going to be, 300 degrees? And you can kind of see the pattern happening here. 30 plus 90 makes 120, plus another 90 makes 210, plus another 90 makes 300. So that's sort of a nice pattern that happens, and you can, again, avoid some of the work. I just don't want anyone to get lost on where these angles are coming from. So, again, I'm trying to find 4 complex solutions. That means all 4 fourth roots of negative 8 plus 8i radical 3. And they are going to be in the form of r cis alpha. So r cis alpha, those are my 4 different alphas, and my radius, my r, is my 4th root of 16. So my 4th root of 16 is going to be 2. So my solutions will be in this form. 2 cis 30, 2 cis 120, 2 cis 210, and 2 cis 300. And if I asked you for those in, I'm going to move these. If I asked for those in polar form, then that's it. You'd be done. That's your polar form and you're good. I'm going to write them out this way since I have more space that way. So 2 cis 30, 2 cis 120, again 2 cis 210, and then 2 cis 300. So these would be my solutions in polar form, or my 4th roots in polar form. And now I'm going to evaluate them to find them in rectangular form. So this would be equal to 2 times the cosine at 30 is going to be radical 3 over 2. And the sine at 30 is going to be a half, so a half I. Multiplying in the 2, I get radical 3 plus 1i. Here it's 2 times the cosine of 120 is going to be a negative 1/2. And the sine at 120 is going to be radical 3 over 2. Again, that's going to be imaginary. Multiplying by 2, I get a negative 1 plus I radical 3 or radical 3i, either way. And I think I've done it both ways in the notes. Here we have 2 times the cosine of 210 is going to be a negative radical 3 over 2. And the sine at 210 is going to be a negative 1/2. Again, multiplying the 2, so we get a negative radical 3 and a negative I. And then lastly, 2 times the cosine at 300. What's cosine at 300 is going to be a half, and then sine at 300 is going to be a negative radical 3 over 2, and again, that one's imaginary. and then multiplying in the 2, you have 1, and then minus I radical 3. And hopefully you can see some connections in these two, right? There's the positive of that and the negative of that. And then here we have the positive and the negative, because these complex roots, the imaginaries, have to come in pairs. Another thing that should sound familiar from college algebra. So these would be the solutions that are in rectangular form. Okay, so if I asked you for the all fourth roots of this complex number, there they are. That would be like you have, imagine the equation. If I said solve x to the fourth equals negative 8 plus 8I radical 3, then you would be looking for all fourth roots of that complex number to get your solutions for x. Okay, so when you're finding all those roots, it would be a process that we could use to find solutions to an equation. So for example, and we're not going to go through all the work here, I just want you to understand what the work would look like. If I asked you to solve x to the 6th plus 1 equal to 0, what would you do? The first thing I would do is look for any real roots. So again, though, if I graph this, those real roots would show up as x-intercepts. But when I graph x to the 6th plus 1, it's not going to touch the x-axis. Okay? So that means there are 6 complex roots. Because my degree is 6, their degree is 6, I know that there are 6 complex roots or solutions. Now I went to the graph, I saw none, the graph did not touch the x-axis anywhere, so none of those 6 complex roots are real. So 0 x-intercepts tells me that there are 0 real roots, which means that all 6 complex roots are non-real or imaginary. Okay, so just to give me an idea of what I'm looking for, right? So I know I'm looking for 6 complex solutions. None of them are going to be real. All 6 would be non-real. If I wanted to figure out what they were, think about the work that you would be doing here. Okay, so algebraically, you could subtract that 1 over, and then you would take the 6th root of both sides. So you're looking for some complex number to the 6th power to get you negative 1, which means you're looking for the 6th roots of negative 1. So if you went through all that process of finding all 6 roots of negative 1 using the polar form and our formula, then all 6 of those roots would represent the 6 imaginary or non-real complex solutions to this equation. So how would you do it? You would find all 6th roots of negative 1. They would be the solutions. If that makes sense. And I can't fit that in there. Okay, so this process of finding these nth roots of complex numbers is super useful because it helps us find the solutions to our equations that cannot be solved in traditional like factoring or quadratic formula types of methods. Okay, so we've got the process down. Hopefully it's enough for you to get started on your homework, but as always, if you need any extra help, then reach out. Until next time, take care.